Hello, and I'm going to walk you through some air friction or drag stuff, and give you some insights how we develop equations for it. We're going to start here with terminal velocity. So terminal velocity is the final velocity that a falling object reaches. You could say the max, well no, it's maybe not max velocity, reaches where the acceleration becomes 0. So basically what happens here is you're going to develop enough air friction as you're going fast enough. It's going to be pushing up on you as you're falling down. Gravity's pulling down, but these two forces are going to become balanced, and acceleration goes to 0, and so you reach a constant fall rate. It's called terminal velocity. So let's do a little diagram of how this will look. Free body diagram of an object, of a falling object. Remember to include motion vectors. Okay, so at the drop, maybe we have some mass. V is going to be equal to 0 initially, and we're going to have some acceleration down. It's going to start going downwards, and this is actually going to be equal to a negative g right away. And why is that? Well, we have some gravity down. Okay, and just to remind you, our force of drag is going to be proportional to the speed. Since we have 0 speed, we have 0 force of drag on this free body diagram. So maybe write that one. Force of drag, remember, is proportional to negative v. Okay, so that's how we start when we drop something. Now, we let it fall for a little ways. We're going to have some mass m. We're actually going to have some downwards of velocity v. It hasn't reached terminal velocity yet, so we're still accelerating downwards, but maybe not as much as we were before. And we have the same weight. That does not change. Still the same mass. Now we're moving, so we got some drag that's opposing that motion. Force of drag. All right. At terminal velocity, so we have our little mass. At terminal velocity, our downwards forces are going to be balanced by the upwards forces, or by force of drag. Force of drag. Okay, and we are going to actually have A equals 0. Those forces are balanced, but we're going to be falling pretty fast at our terminal velocity. This is the definition of terminal velocity, basically. Okay, so write a force equation for the falling object at terminal velocity and solve for the terminal velocity. Okay, so we're going to use this as our guide. So use this as our map, how to build this equation. So I'm going to say sum of forces in the vertical direction is equal to NA. And maybe we'll say down is the positive direction. That'd be fine. We actually don't have any acceleration at this state. So basically I can say my ups are going to be equal to my downs. Force of drag up is equal to my weight, all of it and all of it. My force of drag equation is going to be dv bv equals mg. Now please don't worry about the negative sign right here. We've already accounted for it's moving downwards, and so the force of drag is going to be opposing that. That's the only thing that this means. So we've already accounted that it's opposing the motion direction. It's the opposite direction of this, so we're good. You don't need to worry about that here. This is actually going to be the terminal velocity at this moment where there's no acceleration. And so if we want to solve for our terminal velocity, that's just going to be equal to mg over the coefficient that models the fluid dynamics of that system, B. And maybe we should just say that again. So this B is a constant that summarizes the effects of the viscosity of the liquid, the size of the object, and the shape of the object. And those are all constants. So this is just some constant that describes those things. If you want to learn more about that, take fluid dynamics in college. Okay, so we get to this equation right here. And that's our terminal velocity. And over here we say, can terminal velocity ever be positive? So I guess if we're saying positive is the up direction, maybe this is positive y-axis over time. Okay. Well, this is the positive y direction is up, and this is the negative y direction. Terminal velocity, you're never going to reach it if you're going upwards, because what would be the case if you're going upwards? Your velocity is up. What would we have? We'd have weight down. We'd have drag opposing that. There's no way we could ever get balanced forces and zero acceleration. Acceleration is going to be a big leg. It's going to try to really slow it down in this case, right? So there's no way we could ever get a zero acceleration if it's going upwards. This is only a downwards thing. No would be the answer to this. Okay, so let's develop some equations for how we can model the position, velocity, and acceleration of a dropped object while considering air friction. So velocity is the function of time for a dropped object. Graphs of a drop with drag. Know how the motion behaves over time. Be able to tell the story graphically. Significant parts of the graph. Anticipate these things. Anticipation can make a world of difference for how easy or hard something is. Okay, so when we're thinking about end conditions, this is a drop. V initial has got to be equal to 0. Okay, so that's something we can test when we develop our equations. And it also, we could say, we might have a asymptote of maybe a negative terminal velocity, maybe something we'll see also. Initially, our acceleration is equal to a negative g. And maybe our acceleration is going to go to an asymptote. Oh, there's a P, yeah, of A equals 0 for this. So maybe that goes towards 0. And remember, we saw this. We're just looking at our initial condition right here and our final condition right here. We know where it's where it's going to go. It's going to end at terminal velocity and 0 acceleration. It's going to start with 0 velocity and it's going to go towards, it's going to start with a negative g of acceleration. So that's what we're talking about here. Our equations that we develop should reflect this when we put in time of 0 or time of infinitely long. And then our other thing is that these graphs, all of these graphs should look gradual. They're not piecewise. They're a gradual transition between these states, your starting and your ending conditions. Okay, gradual or smooth. so there's some things to anticipate. So think about how it starts and finishes, and this will help you with your graph. So let's make for a drop with drag. Let's describe its change in words. Okay, so it starts from rest and gets faster over time to reach some constant speed. It's going to reach a terminal velocity. Okay. Acceleration versus time. Describe this change in words. Okay. Well, it's going to starts with a downwards negative g of acceleration and eventually ends at a equals 0. Okay, so let's go ahead and do those things. So here we are. It's a drop, and by the way, so we're going to drop a ball. We're going to say up is the positive direction, and it's going to, we're going to start with v0 equals 0, and it's going to go down, down, down. Okay, so this is a velocity graph. So we're going to say it starts here, and there's going to be maybe some negative VT, some terminal velocity that depends on the mass of the object and its shape and the fluid it's falling through. Okay, and so we're going to make an asymptote line here. Okay, and so it's going to start at well, what's the slope? It's a negative g initially, right? So this is going to have a downwards negative slope initially. It's going to be accelerating quite fast. And then what's going to happen? It's going to end at 0 acceleration. So that's going to be a flat slope. It's going to end up going towards this asymptote like this, okay? And remember, these are gradual, smooth transitions. So it's going to start like this and go woo, like that. Okay, so we got our velocity graph done. 0 acceleration, negative g right here, starts at 0, goes towards some terminal velocity in the downwards direction. Now graph our acceleration graph. Okay, so what does it start with? It starts at a negative g right here. So that's our starting place, right? Up here, right? It starts at a negative g. It goes towards 0. So that's because our forces, as this thing goes faster and faster, remember, our force of drag is proportional to the speed, right? And so it's going to balance out those forces and have the net force go towards 0. Therefore, the acceleration goes towards 0. Something like this. Okay. So let's derive our equation for velocity as a function of time. For a dropped object with drag, we're going to use the king of all physics, Newton's second law, forces, to help us figure this out. That's how we're going to start. That's a little seed we're going to plant to grow this equation from. Okay, so this will describe the motion anywhere along the drop of an object. So our force equation. Let's do a free body diagram real quick here again. We already made one, but so anywhere along here. So at some point in the drop, our mass will have a constant weight. And if it's at some speed or velocity downwards, it will have some amount of drag, force of drag. And before it gets to our terminal velocity, it must have downwards acceleration until it reaches its terminal velocity. It's going to be going faster and faster. These two vectors must be pointing in the same direction. Okay, we're going to say up is the positive direction. Okay, so we're going to keep this in mind for our stuff. So we're going to use this as a map to build our force equation. Newton's second law says sum of forces in the y direction makes my mass accelerate. So I'm going to say my mass will accelerate. Okay, now I'm going to leave the sign on this as a positive, and we'll let our forces tell us which direction this is accelerating. Because the way I do this, we'll write this one equation for a drop, but this is going to be the same structure we use if we throw something upwards or if we throw something downwards initially. And so we're going to let this acceleration respond to what the forces are doing. Okay, and so I have what? I got a force of drag minus the weight. Okay, if I go a little bit further with this, I can say I have my acceleration is going to be equal to negative BV minus mg. So I'm going to use a robust sign on this. I'm going to let this force of drag respond to whatever this velocity is doing. If it's going downwards, then this negative sign will force this to be a positive force of drag. So I'm going to the way I'm going to model this is let my negative sign handle what's happening with this velocity. Okay, so we're looking pretty good. We want to make this a differential equation, though. A differential equation is an equation that has a variable and the derivative of its variable in the same equation. And so that's going to show up with this acceleration right here, because I can rewrite this equation as dv dt is equal to negative bv minus mg. Okay, now I have a variable and the derivative of the variable in the same place, in the same equation. All right, so the next thing we need to do is something called separation of terms. Now, you'll see people do this different ways, and it really doesn't matter. As long as you're not breaking any rules of mathematics, you can move constants wherever you want, but this is the way I find it easiest to do. You'll find people do it different ways if you go look on the YouTube and look for different videos with this, but this is how I'm going to do it. So separation of terms means you need to get all of your v things on one side and all of your t things on the other of the equation. So I'm going to go ahead and start diligently working at that. So I could rearrange this equation to look sort of like this. dv dt is equal to, what are we going to say, negative 1 over m times bv minus mg. Oops, plus. Okay, so what I did here is I factored out these two negatives to the front. There it is. I left these two terms positive. I moved this m to the other side by dividing on both sides. Next, I'm going to officially separate my terms. So by the way, here's a v, and there's a v, and here's a t. We don't want those together on the same side of the equation. We want to separate those things. So I'm going to get dv is equal to, dv divided by this stuff is equal to negative 1m dt. there's my V's on the left side and my T's on the right side. My terms have been separated. Okay, now we're going to do some integration. So let's try that out. So I'm going to integrate both. Okay, it's an equation. If I do the same thing to both sides, it should still be equal. So I'm going to integrate both sides. Integrate the left side, dv of dv plus mg equals the integral of -1 over constant integral dt. So this is t to the 0th power, basically. We're going to integrate from our starting velocity to any velocity afterwards. And that's going to correspond to our starting time of 0 when we first start looking at this thing, to any time t later that corresponds with any velocity v later. So we're going to generate a velocity function that for any time t. Okay, so we're doing fine. When we do this integration, and you can look this up on your integration tables or whatever, you can do it in your TI-89. I'll show you how to do that. But basically, you're going to get out of here 1 over b, natural log, absolute value of b v plus mg. Absolute value evaluated from 0 to v is equal to, this is the world's easiest integration problem, -1 over m, all that times t. When you plug in 0 for t, it's a 0, and when you plug in 0 for this t that you're going to make, it turns a 0. And then when you plug in t for the t, you're just left with this. The 0 term cancels out. All right. So what do we do next? We need to work diligently at getting this v by itself. So how are we going to do that? We're going to run our limits through this stuff. So let's try that. Okay, so when I run my limits of 0 and v through this stuff, I just bring that 1 over b out in front, and then I run my limits through this. V turns into v, and then my lower limit, that v turns into a 0, and 0 times anything is 0. And so we can come over here and draw what we're left with there. Okay, so I moved that b over to the right-hand side by multiplying on both sides. That's how it ended up here and disappeared from over here. And when you have a natural log minus natural log, you can make that equal to the natural log of this thing divided by this thing. And that's how I got to here. Okay, at this point, you can get rid of this natural log by doing e to both sides. And that's going to do some cancellation here. And from that point, we are going to get something like this. I can move the mg to the other side by multiplying by mg on both sides. And there's our variable. We want to get a velocity as a function of time. So look, we've got it pretty good. We're just a few little algebra steps away. We can get velocity as a function of time. We're just going to move all this stuff over. So we're almost there. And so we'll do the next little step right here. Maybe I could have v is equal to mg e negative v mt minus mg. And then we could divide everything by a b. And that would take us over here to, oh man, look. We're so close right now. Cancel. V is equal to, and did we come up with this equation for terminal velocity? Wasn't it mg over b? Remember that? We had that up here, didn't we? Thought we had that. Oh yeah, right there. Okay, so it's all starting to happen. This is so beautiful. So instead of mg over b, I could write vt and actually have mg over b in two different spots. So I'm just going to factor that out. And I'm going to have what? I'm going to have e to the negative b mt minus 1. And I don't know. We could do something kind of tricky here. I'm going to factor out a negative 1 out of here. My terminal velocity, after all, is in the downwards direction. And that would leave me with 1 minus e to the negative b mt. Woo-wee! And this is the thing. This is our equation. Velocity as a function of time is this equation. Wow. Okay, so what are some consequences of this? Let's test it. Use what you know about the initial and final conditions to compare it to the graph. Okay, so what we know, our graph for velocity should look like this. It should start at 0 and it should end at negative vt. Let's see if it happens. Oh, okay, here we go. Let's plug in v of 0 in here and see what happens. So we have negative vt, okay, 1 minus negative b, oh shoot, okay, negative e to the negative b mt. Okay, so, we're going to put in a 0 here for time. So let's put that in. To the 0th power. Doesn't that just make this whole thing go to 1? And what's 1 minus 1? That's equal to 0. Jackpot City. Okay. All right. So what happens if we put infinity in here? Let's try it out. Infinity is equal to negative vt 1 minus e to the negative b, oops, m, that's a b, oh man, I gotta fix that, there you go, b, to the infinity, right? Well, when you have something to the negative power, it's really like it's on the bottom, and if you take something to infinity, that just makes it infinity, and so it'd be 1 divided by infinity. This thing, whole thing goes to 0, doesn't it? And so what do we get out of here? Oh, you reach a negative terminal velocity. Heck yeah! All right, we have checked that our equation we developed is legit in how it functions. So yeah, we just made the mathematical equation that matches this, which is kind of cool. And where did we develop it from? We developed it from our old buddy, a free body diagram in Newton's second law. Man, that is such an important thing. And what's really interesting about this is, I don't know, maybe you're not into drag and all this stuff, but maybe you're into electronics. And these graphs and these equations mirror exactly how capacitors store charge in them and how current flows through circuits. And so if we can understand drag, we can understand complex circuits too. And that's really important. Okay. All right. So the next thing we're going to do is figure out our acceleration equation. So to get acceleration, we're just going to take the derivative of the velocity function. And so let's write that out real quick. So here's our velocity function. We're going to take the derivative of this. So we don't have to worry about this constant. We're going to take the derivative of 1, which is 0. And then we're going to take the derivative of this e function, which is pretty straightforward too. Okay, now I'm going to flip it back to what the terminal velocity was. It's mg. We need to do that because it's going to cancel out some stuff here when we take the derivative. Here comes the acceleration function. When we take the derivative of a constant of 1, we get 0 out of there. Okay, and when we take the derivative of an e function, basically the exponent drops down in front. Remember, we still have this negative sign, and then you still have the e stuff left over. And so, oops, do you know what I need to do? I need to switch this over. We switch this over to our mg over b stuff, right? So this is m, oops, do it in blue here. Mg over b stuff. Yeah, okay. So now when we look at this, we don't have to worry about this little bit here so much. And these two guys will cancel out. And this m and this m will cancel out, and this b will cancel out. And so what are we left with? A bunch of stuff went bye-bye. We are left with something that looks like negative. We have one surviving negative sign. What, we just got a g left there? E to the negative b m to the t. Oh, yeah. G has the units of meters per second squared, and that's what kind of function we're doing, right? And yeah, we're right there. So that's our equation for this. So let's test it out. Okay, so a of times 0, what are we going to get on this thing? Negative g e to the negative b over m times, where t is equal to 0. Anything to the 0th power is just 1. So this is just a negative g right away. And heck yeah, that matches what we said. It should be initially at a negative g because that's the only weight acting on this mass. Very good. Okay, so testing the boundary conditions is so important. Okay, let's test infinity in there. A at infinity for this thing. This could be negative g e to the negative b over m to the infinity. And really, e to the negative is just e on the bottom of a fraction. And so if the bottom of a fraction goes towards infinity, that's going to be like go towards 0, right? And so this is going to be 0, which totally matches our insights on what must happen here. Okay, cool. So there's how you do deriving the functions for velocity and acceleration based upon your free body diagram. We can do that for throwing something up or throwing something down also, and it works very similarly. And if you wanted to get the position as a function of time, guess what you do? You would integrate this velocity function to get that. And that wouldn't be so hard either, would it? Okay, thank you for watching. Have a great one. Bye.